Welcome back to my favorite universe. Today, we're going to spend the entire lecture in defense of a very famous theory known as the Big Bang. In fact, that's the title, In Defense of the Big Bang. I take this time to do it because it's a theory that's so misunderstood by the public. People hear the word theory attached to it, and they say to themselves, oh, it's just a theory, so I don't need to believe it, or there's some sort of discounting of the intellectual achievement that it represents. But I'm here to set the record straight. But before I begin, let me remind you that if you look throughout cultures and throughout time, people, if you look at their writings, have always wondered how things began. Origins, the question of origins seems to be perhaps even genetically encoded in our capacity to ask questions. And we, living in modern times, are no exception to this. Even today, I sit on an airplane and people find out I'm an astrophysicist, and they ask me. It's not the first question they ask. The first is there life elsewhere in the cosmos? Second, tell me about the Big Bang. So it's there. People want to know. And it turns out the 20th century was the very first time in history where we were able to bring the methods and tools of science to answer that question. All previous times and all previous cultures had no greater tools than simply the mythology of their imagination. And so we do live in special times because we're not relegated to just having to imagine how things began. We can look out with our largest telescopes, probe exotic states of matter with our particle accelerators, and come to terms with how the universe began, how it evolved, and how it will end. And so, let's explore the evidence for the Big Bang. Let me begin by saying, what could possibly force a rational astrophysicist to believe that all the matter, energy, space, and time of the universe began 13 billion years ago, packed into a primeval fireball smaller than some infinitesimal fraction of the size of the point of a pin? And it's been expanding ever since. What could possibly bring someone to believe that? Well, the answer is simple. Regardless of what you may have read or heard, the Big Bang is supported by an overwhelming body of evidence. More evidence in support of the Big Bang than any idea that has ever preceded it or any idea that has come since. It's all about the evidence. It's not about belief systems. I've had people come up and say, do you believe in the Big Bang? I don't even understand the question. The question properly worded would be, of all the evidence that's out there, what idea is best supported by that evidence? It's the Big Bang. Now, all this talk about theory. If you look back in the 1900s and the 1800s, the 1800s and the 1700s, there were theories put forth in the world of physics that some of them were kind of radical ideas, but they were finally tested and confirmed, and then they got called laws. Laws. There's the law of gravity, Newton's laws of gravity, Newton's laws of optics, laws of motion, laws of thermodynamics, the era of laws. You enter the 20th century. Very early in the 20th century, we get to Einstein's theory of relativity. In the 1920s, we have quantum theory. We have quantum chromodynamics. There are all these theories. We no longer use the term law. And that's for a couple of reasons. First, these modern theories are as tested and as successful as what were previously known as laws. So we could call them laws if we wanted and be consistent with the naming schemes of our generations past. But what happened in the 20th century is that we came to learn that whatever it is we determine to be true about the universe may only be a subset of a larger truth. And we learned that with Newton's laws of gravity. Newton's laws of gravity and laws of motion describe the environment in which Newton was comfortable, where he had never seen anything move faster than a fast-running horse. So his laws of motion surely accommodated anything that came up in his day. Enter the 20th century, start thinking about the speed of light, high-speed motion, and all kinds of other phenomena take place. We need new theories to account for these new domains in which we're testing how the universe works. And Einstein's theory of relativity does just that. It's a theory of motion and of gravity. And it encloses the piece of the universe described by Newton. It doesn't discard Newton. It enhances the sphere over which the laws apply. So, in modern times when we say law, in modern times when we say theory, if it's a well-tested theory, had that been the same theory around back in the 1800s, they'd be calling it a law, as they'd be calling the Big Bang law. But I will remain humble in the presence of theories yet to be put forth, recognizing that perhaps one day the Big Bang will be enclosed in a bigger picture, a deeper understanding of how the universe works. But the day that happens, we're not throwing away the Big Bang. We will preserve it as a piece of what works under much broader circumstances and under much wider conditions. Now, there's another piece of information we need before we start analyzing the evidence, and that is, we're born and raised with our five senses. Sight, hearing, touch, taste, and smell. You grow up, things happen and you receive them through these senses, and you come to learn, you come to expect things to follow certain sort of rules and regulations. You drop a cup, it falls. Something vibrates quickly, it makes a sound. These things make sense. And the definition of make sense is they are consistent with what we expect to happen given the application of the five senses with which we're born. Enter the 20th century, where science, physics in particular, no longer takes place on the tabletop. We start getting into particle accelerators, exploring domains of matter that your senses had never seen before, whipping out the largest telescopes in the land, looking to the outer reaches of the cosmos, experiencing a scale of the universe unlike anything you've ever seen in your life. So, we start deducing the nature of the cosmos, learning how the cosmos behaves, and it's falling outside of our senses. No longer can we invoke the does it make sense criterion for theories or phenomenon that we see take place in the cosmos. It is long past our capacity to judge whether or not something makes sense. Now, throughout all this, we've always required that whatever is your theory, it ought to make mathematical sense. The math is a logical image of the idea, so that you can then manipulate the idea, ensuring that you're not going to make a mistake in so doing. It's always got to make mathematical sense. But it doesn't have to make intuitive sense, because your intuition was carved in the wrong place. So let's also demand that if you come up with a new theory, it's got to agree with the evidence and predict things that maybe you hadn't known before. Otherwise, it's just sort of an explanation that comes after the fact, putting pieces together without giving you new insight into how the world works. For the Big Bang in particular, a variety of experimental pillars support its status as the most successful theory ever put forth. And I call them pillars because the thing is resting on these pillars. Big Bang makes three assumptions, out of which all the predictions that it makes follow. One assumption, although it knew this at the time the theory was put forth, is that the universe is expanding. Second assumption, yesterday the universe was hotter than it is today. So that if you turn the clock back and you somehow found a way to measure the temperature of the universe, you'd get higher temperatures than now. And it also asserts that the universe had a beginning. That's all it needs. Those three assumptions. By the way, if it explained everything we knew and had 1,000 assumptions, that's not a very good theory. The theory should have the fewest number of assumptions possible, That's what gives you confidence in its power. So, let's take these one by one. Well, 1929, Edwin Hubble of Hubble telescope fame discovered that all the galaxies, except for just a few that are sitting right as our neighbors, all the galaxies that he saw in the nighttime sky had speeds, high speeds, and all those speeds were moving away from the Milky Way galaxy. All the galaxies, except for a handful right closest to us, were expanding away from us. That's something he noticed. Now, he also noticed that galaxies that were twice as far away were receding from us twice as fast. 3 times farther away, 3 times as fast. So it wasn't just sort of a uniform expansion. There was this sort of, the stuff farther away was moving faster. And you ask around, that's a signature of what? In fact, that's a signature of an explosion. If you study the debris tossed in any explosion, what you find is some debris landed twice as far away as the other debris. Yet it all settled at the same time. So it meant the farther debris had twice the speed as the debris that was only half as far. It is the signature of an explosion. And we also learned, 13 years before this, Albert Einstein put forth a new theory of gravity, general relativity. General relativity generalized the premise of the assumptions of what went into his special theory of relativity. Special theory had constant motion and there were no accelerations. There was no discussion of gravity within it. Gravity causes accelerations. And so it was an important special case of a broader story called the general theory of relativity. In the general theory of relativity, he noted that space, the space through which we walk, actually can be thought of as a fabric that distorts in the presence of matter. And the distortion is what we call gravity. And this expansion of the universe was not a galaxy moving through a pre-existing space. Under the tenets of general relativity, the space and the galaxies within it are embedded together, and it's the fabric of space that's expanding. Like some kind of three-dimensional rubber sheet. Now you say, that doesn't make sense. But it doesn't have to make sense, like I said. We're talking about modern physics here, and domains that don't happen in your everyday life. It didn't happen in the sandbox when you were growing up. General theory of relativity, 3 years after it was proposed in 1916. In 1919, it was already tested. Sir Arthur Eddington, a well-known astrophysicist in England, went on an eclipse expedition, waited for the sun to be blocked by the moon, saw stars come out in its vicinity, measured the exact positions of those stars right near the edge of the sun. You can't see them when it's not an eclipse, so obviously he needs this condition to make the measurement. Wait 6 months later, take the same measurement, and notice that the stars were in different places. During the eclipse, the light came past the limb of the sun, and its trajectory was altered because the curved fabric of space and time in the vicinity of the sun, just as predicted by Einstein's relativity. And so relativity, as exotic as it was turning out to be correct. And that while individual objects curve space-time, the whole universe, the sum of all the objects in the cosmos, curves the entire cosmos. And the space is something that has structure that can expand, or that can curve, or that can warp. And galaxies are embedded within that space. So it's consistent with relativity. Now, how do we really know that distant galaxies have high velocity? Well, we measure something akin to a Doppler effect. That's like the police radar gun. They aim the gun at you and they measure your speed of approach or speed of recession. In the galaxy, you perform a similar kind of experiment using light, light of any kind, and you notice that features in the spectrum are shifted towards the red part of the visible spectrum. You have red, orange, yellow, green, blue, violet. If there's any feature in that spectrum that belongs attached to a particular color, if an object is receding, it has shifted towards the red part of the spectrum. We call it a redshift. The farther away the object, the more the redshift is measured to be. Well, if you're receding fast, general relativity predicts that there's something called a time dilation for events that take place at these great distances. I'm moving away from you, and let's say I'm counting out seconds. I say 1, 2, 3, 4. Fine. But if I'm receding from you, counting out seconds, every second that I lay down, the next time I tick out a second, I am farther away than I once was. And that signal doesn't get to you until later. So that the duration of a second is actually increased according to your capacity to measure. It's called time dilation. It's a prediction of general relativity. Sure enough, we have a way to measure this without actually going out into space. There are these objects called supernovae. Here's an example of one in a nearby galaxy. It's that bright star in the bottom left corner of the image. Looks like a star that's brand new on the scene, but in fact it's a dead star. It's the explosive death throes of a high-mass star, thrusting its chemically enriched guts into the galaxy. Sometimes they are so bright they rival the luminosity of the 100 billion stars in the galaxy in which it resides. We understand these beasts. We know how quickly they gain in luminosity. We know how slowly they decline. We know how long that takes. Well, let's look farther out in the cosmos. We look farther out, we find much more distant galaxies, now much smaller, and they're just smudges. They got supernova too. Look in each one of these images, you see a bright star rivaling the brightness of the rest of the system. These supernovae are far enough away so that this effect of general relativity can be measured. And so we look at their rise in brightness and their drop off. And we say, you know something? All the nearby supernovae rise up and drop down in this much time. But these, they take longer to execute the course of brightening and dimming. Maybe it's a different species of star in the early universe that just has a different property. Maybe. But let's figure out how much longer this, what we call light curve, lasts. Calculate that. That's easy. You just measure it up. Wait a minute. How much time dilation is general relativity predicting for a galaxy at that distance? It's bang on. It's exactly what we measure with the stretching of the light curve of the supernova. So we measure the time dilation. That's real. No doubt about it. Now, let's put this together. We've got an expanding universe. We've got galaxies embedding in space. We've got a theory to account for it, the general theory of relativity. There's a brilliant man back at he was around at the turn of the century, but the work for which we remember him was conducted in the 1930s. Here is a Jesuit priest, Georges Lemaitre, a Jesuit priest and cosmologist. Impressive things to have on your business card. He was the first to connect the new theory of relativity, the new discoveries of Edwin Hubble, and the fact that you've got galaxies sort of embedded in this expanding system. He was the first one to think, if we're expanding, maybe in the past we were smaller. And if we were smaller, maybe we had a beginning. Just maybe, the universe had a beginning. And maybe, based on his knowledge of physics, maybe the universe was hotter at a time when it was much more compressed. If you ever pumped up air into a bicycle tire, you feel the valve, it's hot after you've done your pumping, compressing air into a smaller volume. Let the air out with your thumb. If you don't have a bicycle, just try it on a car tire. It works too. And the air comes by, it'll feel cooler. Rapidly expanding air drops a little bit in temperature. So the expanding universe is dropping in temperature. It operates under similar physical principles. So if you turn the clock back, let's look at the universe. It was hotter, 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 and hotter. And there's a point where it was about 3,000 degrees. 3,000 degrees, well, you're aglow. And if you're 3,000 degrees, atoms are ionized, which means the electrons are detached from their host nuclei, and they're sort of swimming in this soup. Light tries to move through the medium, and it gets batted back and forth, so that light does not travel in straight lines through the universe. It's kind of a fog of light, actually. It was 3,000 degrees at a particular time in the history of the universe. And all times before that, the universe was opaque. But at that point, as we cool through those temperatures, electrons combine back to the atoms. And light freely flows through. Well, it's been a long time since that has happened. The universe is 1,000 times bigger, in fact. How much cooler should we be? Turns out it is proportional. So we're 1/1,000th the temperature that it was back then, now being 1,000 times larger. It was 3,000 degrees then. Right now, the temperature of the universe is 3 degrees Kelvin. Kelvin is the absolute temperature scale. If you're 0 on the Kelvin scale, there's nothing colder. 0 on Celsius, you got colder temperatures. 0 on Fahrenheit, it's really cold, but you can get colder. 0 on Kelvin, that's all she wrote. 3 degrees Kelvin in the universe. That's the measured temperature today. This bit of arithmetic was actually first done by George Gamow after the Second World War, in 1948. He proposed, he said, if the universe were hot, we know enough about particle physics now. We had just finished the war effort and the Manhattan Project, building the bomb, getting inside the atom. We knew enough about the atom and about particles and particle physics to know that particles behave in particular ways under particular circumstances. And the electron would jump out of the atom and back into the atom. Light would be released. He predicted what the temperature should be today. He said it'd be about 5 degrees Kelvin, plus or minus. He got the wrong answer, but his idea was right. And at 5 degrees, are you emitting visible light? No. Your photons are primarily microwaves. So he said maybe someone will look around for this signature of the Big Bang, and it would be found in the microwave part of the spectrum. And in fact, in 1967, 19 years after he proposed this, after he made this prediction, 2 physicists at Bell Labs, Arno Penzias and Robert Wilson. You know, Bell Labs, it's the communication center of the United States. It's where much of modern technology that we use to communicate with each other was invented, including, for example, the transistor. So they're trying to measure what signals of microwaves exist in the sky that might interfere with your ability to use microwaves to communicate. So they brought out their antenna, and they're measuring, well, there's a hiss over here, we know what that is, let's remove that. Oh, there's a little signal over here, let's remove that. And they removed everything they could possibly find, but there was still a signal left over. They couldn't remove it. And it was everywhere, no matter where they looked. It didn't focus in one direction and not another, it was everywhere. So they published it. They said, excess microwave signal everywhere we look. They were not cosmologists. They were sort of engineering physicists. It took other physicists to look at that signature and say, you've discovered the Big Bang. The remnant, the visible remnant, now redshifted to microwaves. So redshifted is out of the visible spectrum, past infrared, all the way into microwaves. It has shifted into that part of the spectrum, and is what was predicted by George Gamow, and you have just seen evidence of the birth of the cosmos. They won a Nobel Prize for that discovery, even though they didn't know what they had found, which is kind of cute. They slipped into the Nobel Prize, but somebody had to discover it. Now, how do we know that the microwaves actually come from the edge of the universe? Maybe they're scattered, maybe they somehow a property of space. So if you look between here and there, you'll see a little less than if you look between there and there, because you're not looking through the whole distance. Well, there's a way to test for that. There's a way to test for that. In fact, let's look at a cluster of galaxies right here. This image is it has that sort of you see the chevron there because this is the shape of the detector for the Hubble Space Telescope. Just happens to have that little bite taken out of it. But this is an image of a cluster of galaxies. Every smudge in here is a galaxy. We know that clusters of galaxies have gas within them that is extremely hot, so hot that it's radiating X-rays. Well, if you're microwave light minding your own business coming from the edge of the universe and you come upon one of these clusters, that high temperature microwaves actually gives you a kick. It bumps up your energy just a little bit as you move through the cluster. The prediction is that if the cosmic microwave background is truly in the background, every place where you see a cluster, the microwave signature is going to be a little warmer for having passed through it. The X-ray feature, this is a picture with the Chandra X-ray telescope, and you see this glowing gas. You see also a signature of black holes. The two bright spots, those are black holes in the centers of galaxies, but all the rest is gas. Sure enough, everywhere we look, every sight line in the sky that passes through one of these clusters that has a hot intra-cluster X-ray emitting gas, the cosmic microwave background is pumped up a little bit in its temperature. So that tells us that, in fact, this stuff is coming from beyond every piece of matter that we see. That's an important distinction. Now, is there another way to know that it was hotter in the past than today? That's one of the predictions. Sure there is. There are galaxies out there that, if you look far enough back in time, which is just by looking up, you're looking back in time, because it took light time to reach you, find a galaxy anywhere you want. Go back in time 1 billion years, 2 billion years. Whatever time you go back, the universe was hotter then. And there's a molecule, the cyanogen molecule, CN, that gets excited when taking baths in microwaves. And the higher the temperature bath of microwaves, the higher is the excitation level of that molecule. So we can measure that here, and you say, oh, you're excited by how much? What's the bath that you're exposed to? You measure it, it's about 3 degrees. Find that cyanogen molecule at a distant galaxy, measure it, 10 degrees. Is that consistent? Well, figure out how much the size of the universe changed between now and then. Correlate it with temperature, flip in the equation, bam. It's exactly the temperature of the universe at that time. Smoking gun. What else do we know? The universe was born with a lot of hydrogen and 10% helium. Born that way. So we'd expect every nook and cranny of the universe to have no less than 10% helium. We looked, because that was predicted. That's predicted out of the early universe nucleosynthesis, the early universe particle physics. Regimes of laboratory physics tell us what was going on then. And it predicts 10% hydrogen atoms, helium atoms, anywhere we look. You could have more, but nobody's going to have less, because that's what you were born with. And we look around, look under the table, look around the galaxy, and no matter where we look, everybody's got no less than 10% helium. No less. That's a smoking gun if I'd ever heard one. And there are a couple of other elements, lithium and deuterium, made in trace amounts. They have the opposite problem. They're not made in any great way after the Big Bang. In fact, they're easily destroyed. So what we look for there is, you don't expect more than what we were born with, because natural phenomena in the universe destroy it. So you look around. How much was predicted in the Big Bang? Look around. Do you see any more than that? No. Look in the same haunts. Nope. Nope. Nowhere. So we have two predictors that actually work in the opposite directions. The helium, no less than 10%. The lithium and deuterium, no more than their minuscule fractions. We don't expect any more than 1 in 100,000 hydrogen atoms to be deuterium. Deuterium is just a version of hydrogen that has an extra neutron in its nucleus. We didn't just make this stuff up. There's an unprecedented marriage of astrophysics and particle physics. And a coherent picture has emerged by the application of those two disciplines. And when you combine them, it tells us that the galaxy velocities are real. The galaxy distances are real. The expanding universe is real. Relativity is real. Quantum mechanics is real. The early universe was hot. And the Big Bang is law. But all is not golden. There's some problems that worry all of us. 90% of all the gravity in the universe comes from something that we don't even know what it is. We call it dark matter. We don't know what's causing it. Also, the future expansion of the cosmos will be driven by some phenomenon that acts opposite the sense of gravity. We call it dark energy. We don't know what it is. It's like an anti-gravity pressure. We don't know what that is. By the way, there's a place for it in Einstein's equations. But just because it has a place in the math doesn't mean we understand the phenomenon. Big Bang doesn't know. We can't use the Big Bang to tell us what happened before the first 10 million trillionth of a second. That's a long time ago. But at that moment, general relativity and quantum mechanics break down. They're incompatible at times before then. We need a new theory to get us before that. Big Bang also doesn't tell us what happened before the beginning of time itself. Do we throw away the whole theory just because it doesn't fit? No, that would be unwise. Had we done the same thing with Copernicus, who put the sun back in the center of the universe instead of the Earth, and had planets orbiting in perfect circles, he got the basic idea right. The details are wrong. The orbits were ellipses, not perfect circles. But you don't throw away the whole idea if the idea has, if in its soul, is the correct thing going on. Then you fix the details around the edges. But I look forward to the day when maybe a new theory supplants the Big Bang. And the Big Bang is just a part of a bigger story. And there's one going around right now, where you look back early enough, this sort of quantum foam, this gurgling of the early universe in its earliest times actually spawns different universes, an unlimited number of universes, bubbles growing out of this hyperspace, if you will. Our bubble happens to be our universe with our laws of physics. Other bubbles might have different laws. Maybe in that universe it's incompatible with life. So we're not there making these statements. We're here. And in that case, the beginning of our universe is just part of this long-going, long-running phenomenon, making baby universes daily. There's not much evidence in support of those ideas, but they're intriguing nonetheless, and they are consistent with some major tenets of relativity. So let me leave you with some thoughts. First, whether or not you like the Big Bang is irrelevant. It's consistent with the data. And the data overwhelmingly support it. Nothing's ever come close to describing how the universe is structured. Nothing's ever come as close as the Big Bang. And science does not discard successful theories. It enhances them. And I leave you with a quote from Max Planck, a famous physicist, from 1936. He said, "An important scientific innovation rarely makes its way by gradually winning over and converting its opponents. What does happen is that its opponents gradually die out, and that the growing generation is familiarized with the idea from the beginning."